Lecture number 10B. In this lecture, we will be doing some non-ideal regenerative Brayton cycle with intercooled reheating and regeneration. Again, a solve example. Example is from example number 9.4, Applied Thermodynamics for Engineering Technologies, and that's a fifth edition by McConaughey. A 5,000 kilowatt, 5 megawatt gas turbine generating set operating with the two compressor stages with intercooling between the stages. The overall pressure ratio is 9:1. A high pressure turbine is used to drive the compressor and a low pressure turbine drive the generator. The temperature of the gases at entry of the high pressure turbine is 650 degrees centigrade and the gases are reheated to 650 degrees centigrade after the expansion in the first stage of the turbine. The exhaust gases leaving the low pressure turbine are passed through a heat exchanger or a regenerator to heat the air leaving the high pressure steam stages of the compressor. The compressor has got the equal pressure ratio and the intercooling is complete between the stages. The air inlet temperature to the unit is 15 degrees centigrade. The isentropic efficiency of each of the compressor stages is 80% and isentropic efficiency of the turbine is 85%. The heat exchanger or the regenerator has got the thermal ratio or the effectiveness as 75%. A mechanical efficiency of 98% can be assumed for the both of the shaft, power shaft of and the compressor turbine shaft. Neglecting all the pressure losses and change in kinetic energy, we have to calculate the thermal cycle efficiency, the work ratio, and the mass flow rate. So it is a example of again one stage of intercooling and one stage of reheating. But now in this case, like the compressor and the turbine are not isentropic, but there is irreversibility in it. Intercooling, although is complete, and also the reheating is at the same temperature. Also, there's actually another thing like the one of the turbine, which is the one of the stages of the turbine, which is high pressure turbine, is connected to the compressor with a shaft, which has got the mechanical efficiency of 98%, but the total power which is actually generated by high pressure turbine is transferred to the compressor to two stages of the compressor to drive the compressor, while the low pressure turbine is connected with a generator, and that is actually our output from the cycle itself. The regenerator or the heat exchanger, it is calling in this example, has got the effectiveness as 75%. So we need to find out the thermal efficiency of the cycle, the work ratio, and the mass flow rate. In this example, we will be doing this example using the air standard analysis. For the cold air analysis, for the cold air side, we would be assuming Cp as 1.005 kilojoule per kg Kelvin, and gamma for the air would be 1.4. And for the hot stages side, which is actually the combustion chamber and the turbine side, we would be assuming Cp as 1.15 kilojoule per kg Kelvin and gamma as 1.33. Again, we are neglecting the mass of the fuel. So the question is same, and we would be doing using the same method as we have done in the previous lecture, lecture number 8 and lecture number 10. But yes, we have got some irreversibility now, and now we have got some other analysis like air standard analysis in which we'll be using the Cp value. So for that thing, like if I'm using the air standard analysis, we would be finding the temperature at each and every point. So that would be actually a little bit easy rather than actually finding the enthalpy. Anyhow, let's start with the initial condition, and initial condition would be at temperature T1. So if temperature T1 is actually, I think, 15 degrees centigrade, so 288 Kelvin. So temperature T1 is given. So if it is perfect intercooling, so temperature T1 will also be equal to temperature T3. So that is actually enthalpy at T1 all would be also equal to enthalpy at T3 as well. Now it is actually compressing from state 1 to 2. So if I'm compressing from state 1 to 2, isentropic compression, the only thing actually the formula I would be having for the isentropic compression, and also there is actually a pressure ratio, and the pressure ratio given is actually 9:1. So for both of the stages. For each of the stages, I'm assuming like the pressure ratio would be perfect, and that would be 3. That is 9 raised to power 1 by 2. So using this formula, T2 as isentropic divided by T1 would be equal to P2 by P1 gamma minus 1 divided by gamma, okay, minus 1 divided by K, and the previous example as we have said. So T2 would be equal to 394 Kelvin. So using this formula for the efficiency, isentropic efficiency, which is 84% for the compressor. The isentropic work done divided by the actual work done, which in terms of enthalpy would be CPT2S minus T1 divided by CPT2 minus T1. So CP and CP got cancelled. So you have got T2S minus T1 divided by T2 minus T1. Solving this, we will be getting the temperature, which is actually at T2, and that is actually the exit of the first stage of the compressor over here and somewhere over here now. Already said like it is actually intercooling and the compression ratio. Intercooling is complete and the compression ratio is actually same. So assuming again like T4 would be equal to T2. So moving towards the one, so now this is actually I've got the first stage of the compressor. So if I need to find out the work done of the first stage of the compressor, so first stage work done of the first stage of the compressor would be change in enthalpy H2 minus H1, and in terms of air standard condition or air standard analysis, that would be CP T2 minus T1. Um, and that is that come up as 133.1 kilojoule per kg. Now for the both of the stages, if it is like same compression ratio, same pressure ratio, and the intercooling rate, so that would be 2 multiplied by 133.1. So that would come up as to 166.2 kilojoule per kg for both of the compressor. But definitely there is actually some mechanical losses between the compressor and also the turbine, which is actually driving it. So that is actually 2% losses and 98% is shifted. So that mean like, so the work done of the turbine must be a little bit greater than the work done that is actually needed for the compressor. So that is actually from multiplying 2 into 133, that is for both of the compressor, divided by 298, which is the mechanical efficiency of the shaft between the compressor and the turbine. So my work done of the turbine come up as 272 kilojoule per kg. So this is the compressor driving, and these are two stages of compressor. Single stage is 133.1, and then obviously there is 98% losses between the turbine and the compressor. And so I have got the total work done of the turbine come up as 222 kilojoule per kg. This is the work done of the turbine. This is over here. So this is the work done of the turbine from 6 to 7 over here. Now, if I'm looking at the second stage of the turbine, so I do not have got any other value, just the temperature at T8, which is actually temperature at T6, which 60 was there. But again, I need to have a compression ratio or the pressure ratio, which is the expansion ratio as well. So I need to find out the expansion ratio of the second stage of the turbine in order to find out the work done. So to find the second stage compression expansion ratio, I need to go from the first stage. So the first stage data is given, and that is actually I have got the work done of the first stage of the turbine. So if I've got the first stage of the turbine, the formula would be like the work done of the turbine would be equal to CP T6 minus T7. That is actually T7 would be actually the actual T7, not the isentropic. So work done would be equal to 272, and that is actually CP. Now, the CP I'm using over here is 1.15. Um, at this moment, like this is my cold air side, and this is my hot air side. So that's over here I'm using the CP value at 1.005, and over here I'm using the CP value of 1.5 here. The gamma over here is 1.4, and gamma over here is 1.33. So yes, moving towards that one. So CP value is 1.15 over here, 293, which is actually 650 plus the 273. That would be the in Kelvin. Uh, I can find the temperature T7, which is equal to 680 686.5 Kelvin. Now using this temperature, I can use the I can find the temperature T7s. So T7s would be actually found out using the turbine efficiency. So turbine efficiency is the 85%. So that is actually actual work divided by the isentropic work. So actual work divided by isentropic work. So actual work is actually T6 minus T7 multiplied by CP. You understand, like CP is already gone. That is CP and CP. So that will be done like this. So using the efficiency now 85%. So I can find the temperature T7s over here. So T7s, if I have got it, so this is actually equal to 645 Kelvin, and that is actually the this expansion from stage to stage. So T7s is there now. So now I've got the compression, sorry, expansion, which is actually P6 by P7 would be equal to 6 by T7s, which is the isentropic expansion, as the pressure is not dropping. So gamma minus 1, gamma divided by gamma minus 1. That's there. Uh, Using the temperature T6, I've got temperature T7 as well. So I can find the pressure, the expansion or the pressure ratio, which is 4.19 now. Assuming like the total pressure, the expansion or the pressure ratio is 9, so I can find the P8 by P9, which is actually the expansion in the second stage of the turbine, which is from 8 to 9. So I can find the expansion in the second stage, which is 2.147. Now, once I've got the expansion now, so I can move forward to find out the temperature T9 and T9s, and then obviously T9 as well. So now the temperature T8 by T9s would be equal to P8 by P9, P9 raised to power gamma minus 1 divided by gamma. So this is my the temperature, and now I can find the temperature at T9, which is actually temperature at this point now. So temperature at this point, which is the low pressure turbine now. So temperature T9s, and then obviously using the efficiency of turbine as 85%, I can find the temperature at T9, which is would be the actual temperature, which is 786.7. Now once I've got the temperature, once I've got the expansion, or I'm sorry, the expansion I've already used for the finding the temperature. So once I've got the both of the temperature, which is T8 and T9, T8 was given as it is reheated to 650. So I've got the temperature now. So T8 minus T9, that would be, and multiply by CP. So you can find the work done of the second stage of the turbine, and that is actually the work done of the second stage of the turbine would be equal to 153.7. Yes, they have already multiplied with the efficiency of 98%, as there would be actually loss from the generator and the turbine. So this is the network output of the low pressure turbine. Now, moving, this is what actually a little bit complete in this sense. Like I have found the each and for each and every point, I have got the temperature, and also I can find the enthalpy. Now for the regenerator, has got the which has got the effectiveness of 75%, and which has got the temperature which is need to be found out. So let's move to the regenerator now. Regenerator has got the thermal ratio, or the effectiveness, or the heat exchanger effectiveness is actually 75%. So that is actually, if I'm looking at this one, so this is my regenerator installed. So from the air side, the temperature or the air is entering at 4 and leaving at 5. From the turbine side, which is the gas side, the air is entering at 9 and leaving at 10. So that would be the effectiveness would be equal to T5 by T5 minus T4 divided by T9 minus T4. So in here, in this condition, I can the T4 temperature, let me check, like, yes, T4 was given, oh sorry, we have already found T4 over here, which was somewhere, yeah. T4 was there, and T5 we need to find out. T9 is just over here. We have already got it, so we can find T5 over here, and obviously once we have got T5, we can find the enthalpy as well. This is the regenerator side or the heat exchanger side. Now the heat supply, the total heat supplied would be the heat supplied, which is actually from in a reheat, and which is the from 7 to 8 over here, and obviously the heat supply would be actually equal from 5 to 6 over here. The other the heat would be um, in a regenerator. So that heat supplied would be actually equal to Cp, that is actually T6 minus T5, and in a combustion chamber, sorry for that, in a combustion chamber, which is actually T6 minus T5 multiplied by Cp, and in a reheat, which is actually T8 minus T7 multiplied by Cp. Both of the Cp would be actually of the high end, because it is actually on the combustion chamber and reheat side. So heat supply would be 534. So the cycle efficiency would be 28.8%. Ignore this plus a minus sign, because McConkey is using a different symbol for different, like it is using the work done supplied is positive in McConkey, and work done by the system is actually negative. So that's what actually it is. Just the sign convention is changed in McConkey. So 28.8% is there. uh, the gross work, which is actually what would be the total work done. So the total work done would be 272, and that is actually the work done on of the high pressure turbine and the work done of the low pressure turbine. We have already done we have already multiplied this thing with 98%. So just divide with 98% to get the actual work. So that would be the gross work would be equal to 429. So 429 is my gross work. The actual work ratio would be the actual work, which is 153.7, divided by the gross work, which is actually the 35.8%. The electrical output is as the electrical output is 5,000 kilowatt or 5 megawatt. So the mass flow rate would be the work done multiplied by the mass flow rate, would be equal to 5,000 kilowatt. Then find the mass flow rate, which is 32.6 kilogram per second. The current example was done by assuming like all the pressure losses were neglected. But in actual, there is actually a pressure losses in a gas turbine unit, and there is actually pressure losses due to friction, turbulence in an intercooler. There's the air side of a heat exchanger or air side of a regenerator. We have got the combustion chamber losses uh, uh, due to high velocity increase. Um, we have got the heat exchanger gas side of the regenerator losses. In exhaust duct, we have got the pressure losses. So we have already neglected all the pressure losses, But assuming like they in a no, in a normal gas turbine unit, there would be actually pressure losses and irreversibility. So we are actually in actual when we are dealing with the actual gas turbine, we have to consider these pressure losses as well. Now, a little bit quick, moving towards the another example in which we are considering the pressure losses, and obviously solving the same example, which was actually example 9.4, and now assuming like there is actually a pressure losses between in different stages of the gas turbine cycle. So let's solve the example in that way. So example 9.4, and it's continuing with the same book. For the gas turbine generating set, as we have discussed in example 9.4, recalculate the cycle efficiency and the work ratio, taking the following pressure losses into account. By assuming all other assumptions still apply. A side of a heat exchanger, A side of a regenerator, we have got the pressure loss of zero point 0.3 bar. The gas side of a regenerator and the exhaust duct, pressure loss is 0.05. The intercooler has got a pressure loss of 0.15, and each combustion chamber has got the pressure loss of 0.2 bar. Now, taking the ambient as 1.1 bar, let's we and taking the compression ratio as 3:1 as previously calculated, and find the new overall pressure for the compression, and also the other data is entered. So let's start with the actual thing now, or solving the example now. So each of the combustion chamber, if I'm taking each of the combustion chamber, so the combustion chamber is from 5 to 6. So we have got a pressure loss of zero point 0.2 bar over here, and we have got a pressure loss of zero point 0.2 bar over here. For the air side of a heat exchanger, air side of a regenerator, we have got a pressure loss of zero point 0.3 bar. The gas side of a heat exchanger and exhaust duct. So gas side of a heat exchanger is actually from 9 to 10. So that is actually the heat exchanger. We have got the 0.05, and obviously the exhaust duct is actually also, sorry, 0.05, and exhaust duct is 0.05 as well. Um, so this is my gas out of heat exchanger. Intercooler has got the pressure loss of 0.15 bar. So let's recalculate each and everything. The ambient, which is actually a pressure at 1, is taken as 1.01. The temperature was 15 degrees centigrade. Remember that thing. Yes, the inlet condition was actually 650 degrees centigrade. The expansion ratio, yes, the compression ratio is actually 3:1, and we have to recalculate the other thing. Um, Many data definitely would be changed, but few of them would be unchanged, like the inlet condition and the compression at first stage would definitely not change. So state 1 would be there. Temperature, what actually it is, as state 1 was previously, now we have got the same one. Uh, T2S would be the same, which is actually was previously calculated, and also T2 would be same as actually the previously calculated. This was 420 Kelvin. The work output from the first stage of the turbine, 133.1 kilojoule per kg. As it say, like the compression is same, so that mean like the work done of the both of the would be the work done of the compressor would be same. That would be 133 multiplied by 2, and obviously if I'm looking at the high pressure turbine stage, that would be multiplied by 0.98%, so that would remain same. So now the pressure P3, which is actually over here. So we have dropped a pressure of 0.15 in intercooling. But what would be the actual pressure at 3? So the actual pressure, if I'm looking at 3, so from 1, actually I have got a pressure of 0.1. I've got a compression of 3. So that would be 1.01 multiplied by 3. That would give me 3.03 minus the pressure loss, which would be at in an intercooling, which is 0.15 bar. So at 3P3, my pressure would be 2.88 bar. Now moving towards number four, the outlet of the high pressure, which is actually P4. So now the same pressure ratio as it's written that the pressure ratio for each compressor is 331. So for same pressure ratio, I have got the pressure now 2.88 bar. So 2.88 bar multiplied by 3. So the actual pressure I've got at state number 4 or P4. So the actual pressure would be equal to 8.64. So this is the actual pressure. So if I'm looking at the overall pressure ratio, so overall pressure ratio would be 8.64 multiplied by what actually was P1 or P3 over there. So that would be, so 8.64 divided by 1.01. So that is actually 8.55 pressure ratio. That is the pressure ratio. So that is compared to previous, which was 9. So now the pressure ratio is reduced due to the pressure losses in a intercooler. Now moving towards the stage number 6, which is actually the entry of the first stage of the turbine. So at first stage of the turbine, you will be carrying the same, let's say 8.64 is here at 6. Now calculating the pressure at this one. So we have got the pressure losses in the air side of a heat exchanger, or in other words, the regenerator, and also the combustion chamber. So 8.64 minus 0.3 minus 0.2. So we have got the actual pressure of 8.14 bar at the inlet of the first stage of the turbine. Uh, the work output of the high pressure turbine is same as we have previously calculated, and that was 272 kilojoule. And previously again, so the same thing for the same thing, the T7S would remain same, and also P6 by P7 would remain same, which is actually P6 by P7 previously calculated was 4.119. Now we need to find the actual pressure at number 7. So if P6 is already there, which is 8.14 bar, and P the ratio is there, which is actually 4.14. So we can find the actual pressure at number 7, which is over here now. So at P7, I have got a pressure of 1.943 bar. Now moving towards the 8, which the combustion chamber, so sorry, the reheat combustion chamber. So now I have got the pressure losses of 0.2 in here. So 1.943 minus 0.2. So the actual pressure at 8 would be equal to 1.743 bar. So now this gives us like the actual pressure at 8. Now I can find the actual pressure at 9, and also the compression ratio of the second stage of the turbine. So the to find out the actual pressure at 9, a little bit I have to go to the other condition, like, which is actually condition at the exit of the sorry, the exit of the regenerator towards the air, or what I'm saying, like the exhaust duct actually. So at exhaust duct is already say like it is exhausting at atmospheric. So exhaust is actually at 1.01 bar. So 1.01 bar, if I'm calculating this on this end actually, so 1.01 plus 1.05 5 sorry 1.01 plus 0.05, as it was actually lost over here. So that is actually the actual pressure at 9 would be equal to 1.06 bar. This gives us like the pressure ratio P8 by P9 as 1.644. Using this pressure ratio, I can find the temperature at T9S, which is actually T9S divided by T8 would be equal to P8 divided by P9 gamma minus 1 divided by gamma. So this gives us a temperature of 815.4 Kelvin. Using the efficiency formula of the turbine, second stage of the turbine, we can find the temperature at T9, which is actually 831. Now, if I've got the temperature at T9 as well and T8 as well, at high end side, I would say like the low pressure turbine, I can find the work done, and the work done is actually now equal to 105, 105.2 now. And previously, like if you remember, it was 153.7 something. So that's been a huge loss, uh, overall huge loss of the turbine work. So then the usual equation 9.6 for the thermal ratio, effectiveness, and the heat exchanger. We can find the temperature at T5. Now the heat supplied would be actually from 5 to 6, and that is actually the in a sorry not to 5 to 6 over here, and also from 7 to 8. So the heat supplied would be in a combustion chamber and reheater, that is actually 495.3 now, and the cycle efficiency would be equal to now 21%. This is definitely a drop, a huge drop, or 7% almost drop from the previous value, which is 28.8%. Now the gross work is actually now equal to the gross work ratio is now 27.4%. Previously, it was actually 35.8% when the pressure losses were neglected. I hope like you understand this example. If you have got any question, you can actually send me in a Google, my Google Classroom, or you can actually drop me a comment on a YouTube channel. Thank you very much. Have a nice day.